know where there's some. Right here in the hall, clerk.
No, Molly, not in there. I have
Hi there. This is a little chassis from a little GE-514 radio, All-American 5, that I repaired some months back and finally got back to it to do the AM alignment. And but it reminded me that one of the problems I thought I was having with it was the automatic voltage or volume control, the automatic volume control, gain control. Voltage was bouncing all over the place. It turned out that it was one of these peculiar GE solder joints, these wire connectors that they used for a couple of years and stopped, thank goodness. And I say thank goodness because it was a bright idea for the time for automating manufacturing of this, but not at all bright for replacing anything in here. You have to do it all with J-hooks and try to... Anyway, it's very difficult. But it works fine now. But it did make me think...
all that and, winning national championships.
Yeah.
Point of view, but
it picks up our crappy AM around here just fine. But anyway, it did bring me back to the Fundamentals series that I had started, oh gosh, I don't know if it was last year or when, but the Fundamental series, to talk about how automatic volume control circuits work, particularly in this particular All-American 5. All-American 5s, though, are kind of all the same, so if we can figure out how the one works in here, we can probably figure out how the ones work in other All-American 5s too. So let's start where I always start, by looking at the schematic and seeing what it tells us. Before we talk about what's going on in the GE-514 and the All-American 5 radios, let's talk about what came before. This is a schematic for a 5-valve Nucleodyne receiver. This is a tuned radio frequency receiver, generic, and we'll ignore the Nucleodyne part for right now. Most all TRFs had this configuration. Antenna, of course, came into an RF amplifier, the first stage RF amplifier, which was then, the signal was then amplified by a triode and passed on to the second RF amplifier, which is right here. And then the detector, in this one, it has a detector. The detector stage is right here. And finally, two audio amplifier stages, one after the other. Now, the problem with the TRF radios was, well, there were multiple problems. One problem was that to tune them, you had to manage 3 tuning capacitors with knobs on the front of the radio, all at the same time. In order to get a station tuned in, they all had to be tuned to exactly the same frequency, which was a bit difficult and challenging. It usually took 3 hands to tune the radio, plus a 4th hand to control the volume pot, which is over here in the final audio frequency output stage. And the other problem with the TRF radios originally was this triode was a perfectly, it was a miracle of its time, amplified like crazy, but it also tended to oscillate. And so as you're trying to tune a radio station in, this thing would occasionally break out into wild oscillations, and your radio would be screaming at you in your earphones. And all two stages rather, in this case of the RF amplifier, had triodes that would squall like crazy. But the Nutridyne introduced a brand new technology concept. You can see it better on this first stage right here. The first stage is the plate output goes into the primary of the RF transformer right here. And then on the secondary of the RF transformer, you can see a tap right there that goes up here and feeds back in through this capacitor called NC. That was called a neutralizing capacitor. And it fed back into the grid of the triode. And what that did was it would take the signal from the secondary, but down here at the bottom end of the secondary, which was in opposite phase to the primary. Okay, how can we tell that the coils are wound in separate directions? You can look right here and see it. You'll notice that this line here, the coil goes like this, and on this line it goes like this. So those are opposite polarity. And what that means is that as this end, and you can pick either end, let's say that there's a north here and a south here. On this secondary, there will be a north here and a south here. So opposite polarity because they're wound in opposite directions. The GE-514 has its coils wound in the same direction. So in terms of passing a signal from here to here, it really doesn't matter, particularly with AM, because the audio information is impressed on both the positive and negative sides of the RF signal. So as the primary would be going up, down here, primary at this end, oh gosh, it's hard to tell. Primary at one end or the other would be going up. This tapped frequency, this tapped point at the secondary would be going down. So they would take a little bit of that signal that was induced into the secondary and feed it back through this capacitor into the grid, thereby neutralizing the attempts of the triode to oscillate, to self-oscillate. That would neutralize the self-oscillation and the radio wouldn't squeal when you're trying to tune it. So that was a negative feedback loop right here. Take a little bit of signal, turn it over, feed it back to the input. That dampens the input and prevents the tube from squealing in this case. So that's how the Nutridyne solved one problem, was with a negative feedback loop back to control the input signal. So that's the tuned radio frequency receiver right here, very generic one. And I should say that the problem with the tuning, three tuning condensers here, was you're usually listening to these things through earphones. If you had a lot of money, you could buy a speaker, but they're often connected directly to the earphones. And as you're tuning through here, if you hit a faraway station, it was a very tiny little signal, and you'd tune these three things to bring it to maximum. But if you then tuned a little further up the dial and hit one that was right down the street, it would blow your eardrums out. It was so loud. There was no way to control how much things were amplified in this receiver. So then along comes a young man, another of our boy geniuses in the radio business, named Harold Alden Wheeler. And he was 19 years old. He worked as employee number 1 at the Hazeltine Corporation. which happens to be the inventors of the Nucleodyne radio. So what Harold Alden Wheeler did was he figured out a way with heterodyne radios to provide feedback so that negative feedback so that weak stations would be amplified to the maximum and loud stations would be de-amplified or tuned down so they didn't blow out your ears. Let's see how he did that. What Harold Alden Wheeler figured out in 1925 was that if you could provide a feedback mechanism to the prior stages, to the stages prior to the actual audio amplification, you could control the amount of amplification that each stage provided. Now this is the GE-514, and we're going to take a look at this line right here, the automatic volume control line, and we'll see where that gets hooked up. Now let's look at what this AVC line is connected to. The AVC line is connected to the bottom of the secondary transformer in the first IF transformer. Now the AVC signal is DC, and we'll talk about how that's generated a little later. But this is a DC signal. Because it's a DC, it goes up here, goes right through this coil and onto the grid of the 12BA6, thereby controlling the bias of the 12BA6. If the 12BA6 is more positive, it amplifies, or the tube amplifies more. If the control grid is more negative, the tube amplifies less. The AVC line also goes over here to the antenna connections on the 12BE6 and connects through the antenna over to the central grid, the control grid of the 12BE6, the first RF and oscillator, first RF amplifier. So it controls, the AVC line controls the bias on the V1, the 12BE6 amplification stage. So let's figure out how we get a DC voltage, a negative DC voltage yet, right here, when all we've got in this thing is plus 90. We've got a signal ground, and that's all we've got. How do we make a negative voltage? Well, the magic all happens right here. And this is what we're going to look at, is this section of this radio right here. This is the second IF transformer and the detector and first audio amplifier. So it's all here. Here's our 12AV6, here's our second IF transformer, and here's the power output tube, 50C5. So what do we need to know about what's going on here? Well, the first thing we need to look at is the 12AV6. It is a multi-purpose tube. It has two diodes in it. Well, first of all, it has a cathode. This is the cathode right here, this guy. And it connects to, which is important, our signal ground in this case. Now this is not chassis ground, this is signal ground. And I spent some time talking about the difference between these two in the series on repairing and restoring this radio. So check back with that. But signal ground is not the same as chassis ground. Signal ground is the ground that's relative to all the signals that go on in here, is not ground relative to earth ground or to the chassis ground. So we have a cathode tied to signal ground, and that's very important. Right here, you'll see two diodes. They're picking up, or they're adjacent to the cathode. one here, and one here. Now one of them, the lower one, right here, is connected directly to the cathode, and which is tied to ground, which means, in this case, that this cathode cannot influence this plate of this diode because they're tied together. Anything the cathode does, the plate's going to do. And all the cathode is going to do is be at signal ground, so there's literally nothing going on with this second diode. In other applications for detectors, you may see the second diode used. So that's that. The second thing to notice is we do have another diode right here, and that's tied directly to, to our to the upper side of our secondary on the second IF transformer right there. So that's an important thing to note. The third thing is what's going on with the rest of the 12 AV6, and that is it's a triode right here. It's just a standard triode amplifier. If the plate is positive relative to the cathode, then electrons will start to flow from the cathode to the plate. If the plate is not positive relative to the cathode, no electrons will flow that way. The same thing is true of the diode. Let's back up over here. If the plate of the diode, which is right there, is not positive relative to signal ground, which is the cathode right here, right here, then no electrons will flow this way. Electrons will never flow from the plate to the cathode. That's not how diodes work. What else do we have here? We have right here at the bottom side of our second IF, running right down here, we have the volume potentiometer right here. Aside from being a volume potentiometer, it's also a 0.5 or 500 K resistor, and we need to pay attention to that. That's a 500 K resistor running from the bottom side of the second IF to our signal ground. Talk for a minute about the signal is coming into the primary of the second IF transformer, and it's represented very often like this. It's made to look like this. In fact, it doesn't look like this at all. What we're seeing here is the 455 kilohertz going up and down, and this is a sine wave modulating the 455 kilohertz. And we're assuming for the purposes of this video that it's at 1,000 hertz, as a 1,000 hertz tone. But in fact, what it would look like would be a blur of these up and down, of this sine wave going up and down, 455 times as fast as this sine wave going up and down. So to be clear about that, if you're a digital person at all, you can think about it this way: is that the carrier, the 455 kilohertz, has a sample rate of 455 kilohertz. It samples the analog signal 455,000 times per second, while the signal itself, the tone, is going at 1,000 times per second. So these rates of change that you see in these drawings, like I'm using here, are misleading. That's okay. The point of them is that it gets the idea across, and that's what we're hopefully doing here. The second thing I want to talk about is where the signal, it's often called information or intelligence, where it resides, and that is at the peaks of the 455 kilocycle IF frequency. This is the profile, the envelope of a 1000 hertz signal impressed upon a 455 kilohertz signal. So when the volume of the 1 kilohertz signal goes up like this, the volume, the equivalent volume of the 455 kilohertz IF frequency goes up as well. The difference is that this goes up and down and up and down and up and down and up and down many times faster than the 455 or the 1000 hertz tone. The other thing is that it goes up and it goes back negative. Oh, let me back up a minute. The other thing is that think of this as a 0 volts line, 0 volts DC or 0 volts AC. The 455 kilohertz tone, or the 455 kilohertz intermediate frequency, goes up to represent the peak of the 1000 hertz tone, and it goes down to represent the peak of the 1000 hertz tone. In other words, the 1000 hertz tone is represented both in the positive going excursions of this sine wave and in the negative going excursions of this sine wave. So what that means is that our information, our audio sound, is both carried on the top, the positive going peaks of the IF, and on the bottom, on the negative going peaks of the IF. So we have the IF representing the tone, the 1000 hertz tone, twice. Once as a positive going peak, and once it as a negative going peak, and then again and again and again, 455,000 times per second. So I hope that's clear, because what I just talked about will show up next. Let's look at what happens now. I've done this animation, pardon me for the crudeness of it, but it's the best I can do. What we've got over here is a single cycle of the 455 kilohertz IF signal. Its peak represents the volume of the broadcast originally received, whether it's loud. If it's louder, this is higher. If it's quieter, this is lower. Its actual frequency shifts slightly to reflect the frequency of the sound it's captured, the audio information it's carrying, but that doesn't matter for our purposes. What I want to do is follow what happens when this signal comes into the primary of the second IF transformer. Now keep in mind that we have a signal ground here, a B minus line right down here. Keep in mind that this is coming in not as a DC value, but as an AC voltage. AC voltage goes positive and goes negative. So let's see what happens, and I'll step through this and talk about it as we step through, and then we'll animate the whole thing and see how it goes. So at the very beginning, our little red and yellow dot is right at 0 volts. The voltage starts to rise. Oops, can I do this? Yeah, maybe. The voltage starts to rise. As the voltage goes positive, coming into the primary, it starts to generate a magnetic field right here in blue. And I'm labeling it for my own purposes. This end is north and this end is south. The generation of a magnetic field here generates a magnetic field over here in the secondary. And because these two coils are wound in the same direction, it has the same polarity. In other words, north is up here and south is down here. except for my purposes right here, I want to refer to them as positive and negative voltage. So we've got an expanding magnetic field that's generating a positive voltage on this side and a negative voltage on this side. So we'll go a little bit higher, and the magnetic field size and intensity is increasing, and we keep going that, and it keeps increasing on both sides until we hit the peak, the highest voltage possible, the highest input voltage rather, right here from the 455 kilohertz intermediate frequency. Now notice a couple of things. I'll back up a bit. As soon as we started to go positive here, we started to get a positive voltage here, and that's what this diode right here has been waiting for. This diode is waiting for a voltage that's more positive than the signal ground down here. So when we put a positive going voltage right here, the diode starts to conduct. It's not conducting a lot, but it starts to conduct, hence this yellow line. As the signal on our input goes to a higher and higher voltage, the magnetic field gets bigger and bigger, and the amount of current that flows through our diode plate onto the top of the second IF can gets greater and greater, and it expands until it hits peak. At that peak point, we've got the maximum voltage here, we've got the maximum amount of current flowing from ground through this plate, through the coil right here, down through this 0.5 meg volume resistor, volume pot, down to signal ground right here. When our sine wave voltage begins to fall down, the same thing happens, except in reverse. The magnetic fields in both sides of the IF transformer start to collapse. The diode plate is still conducting, but it conducts less and less and less and less and less until it hits zero and no conducting is happening. Now what happens when we go to the rest of the way on this sine wave right here? The answer is not much. As the voltage drops here, we get another magnetic field generating on both the primary and the secondary. But look what's happened to the polarity. Watch the north right here. We hit zero. There's no north because there's no current. We start to go negative, and now we're going in the opposite direction, and south is at the top, and negative voltage is showing up on the top of the secondary. And so we go through this cycle. The magnetic fields get bigger and bigger on the primary side, but no current is flowing through here because at this point, the plate of the diode is more negative than the signal ground down here. Goes down and down and down. Magnetic fields get bigger, still nothing happening. Goes back up to zero, and finally we're back to where we started, sort of. So, what's happened? Let me animate this for a cycle, and you can see what it looks like. So we get for the first half, we get current flow through the plate of the diode down through here. For the second half, the lower half, the negative excursion, we don't get any current through this diode. Now, the interesting thing is we want to pull this voltage off right here. We want to know what this voltage, how this voltage is changing, because the amount that it changes from here to here is the sample, if you will, of the audio signal. We want to know how much that voltage is changing, and we want to do work with it. So as the voltage, as the voltage climbs to its peak. We start to get current flowing through here. We get current flowing through here, and we get current flowing through here. Now, it's an interest. This is where it gets really interesting. Oops, guess I can't get rid of that. Okay, where it gets really interesting because of this negative sign right here. It's positive at the top of the transformer, it's negative at the bottom of the transformer, and it's more negative than cathode ground. Cathode is grounded to our signal ground here. This voltage right here, as this side's going positive, this side's going negative, and it's more negative than here. So what we end up with is a negative voltage right here. Oops, moving that around. We end up with a negative voltage right here at this top of this 5.5 meg ohm resistor. And the voltage that appears here is a reflection of the voltage that it shows up here. So at the peak of this sine wave, this 455 kilohertz intermediate frequency, our voltage here, give or take, is peak as well, but peak negative. It goes negative, and it goes negative further than the B minus signal ground. So this is a negative voltage right here when this one is at its peak. This one is at its peak except negative. In other words, it is a mirror image of what's happening here. This one's going positive at this point right here. This is going negative. Now, when we go negative, when this intermediate frequency goes negative, no current flows because the plate of the diode is more negative than its cathode, therefore no current will flow in this direction, and this is just sits idle. It doesn't do anything, even though the magnetic fields are increasing here. The plate is not energized of the diode, and so no current is flowing through here in particular. So what does that mean? This point goes negative relative to this sine wave going positive. Let's take a look. All right, let's take a look at what's happening right here at this very point in our schematic. This is the top of the volume potentiometer. And we've got, this is the beginning of the AVC line. We've got AVC going back to our left here. IF transformer secondary. So as the IF transformer secondary at the top of it goes positive, the diode conducts current through here. This side, this end to the bottom of the IF transformer goes negative, as it does here in this drawing. So we've got negative going pulses here for every positive going pulse up here, and the extent to which they go negative, the number of volts they go negative, depends on the volume of the incoming signal, the incoming audio signal, in this case 1,000 hertz. So this graph represents what happens right here. Now the other component we have to need to be interested in is this 400 picofarad capacitor right here. It serves two purposes. One is it's a small capacitance, so it's very susceptible to allowing 455, the frequency, to drop right straight through to our signal ground. In essence, it's canceling all this frequency. However, it also serves a second purpose in that it gets charged up as it's doing this work. It charges quickly and discharges slowly through this 0.5 meg resistor right here. So let's take a look at this in an animation. As the voltage goes up, it hits its peak, and then it starts to fall away, but the capacitor keeps it charged up. and fall away again, hits another peak, falls away, hits another peak, falls away, and keeps repeating this because right here is what we're looking at. The red dot represents the voltage right here. So we're seeing a slightly varying DC voltage that represents this signal. Our audio signal is now residing right here at maximum volume. The volume pot, the volume potentiometer, taps into that signal, and as you crank it down this way, you get less volume. As you crank it to the top, you get more volume going off to the triode in the first audio amplifier here. But this is what we're interested in for AVC. This is creating a voltage that varies and drifts around with the peaks. But over time it goes up, averages down, goes back up, averages down, goes back up, averages down. We've got a varying DC voltage right here, our AVC bus, because of this capacitor. The voltage goes through the 2.2 megohm resistor, and you can't see all of it right here, but there's another capacitor right here, 0.05 microfarad, and that's a smoothing cap. That smooths this out so that this voltage reflects, the voltage going to our AVC reflects how loud the incoming signal is. The louder the incoming signal, the greater the negative voltage here, like this. The quieter the incoming signal, the smaller the negative voltage, like this. On this side of this 2.2 megohm resistor is a varying DC voltage that reflects the loudness of the incoming signal. The louder it gets, the more negative this gets. The quieter it gets, the more positive this voltage gets. And it just swings back and forth with the loudness, not necessarily with the frequency. I could say it's kind of a representation of the data as well, but it's smoothed so that it doesn't do the quick changes that you would want at the top of the volume pot. So over here we've got a smooth DC voltage that is controlling the bias on all the previous stages, and when a really loud signal comes in and this goes very negative, this side produces a negative, very negative voltage, and it turns down the amplification of the previous stages. When this side is a very small voltage, this side goes a bit more positive and allows more amplification to happen. So this is our AVC circuit. This is our detector circuit, because we're detecting the audio up here and we're sending the audio off to the right, and we're detecting the volume of the signal coming in and sending that DC voltage off to the left to control the amplification of previous stages. So that, in a nutshell, is our AVC circuit. It's I apologize for this being so long, but I couldn't think of a way. I didn't have time to make it shorter, as some famous writer once said. I hope it helps you understand what's happening in this particular All-American 5. I hope you can learn from this a bit and relate it to whatever radio you happen to be working on in terms of the AM detection and in terms of creating a varying automatic volume control voltage to control how previous stages amplify. So I hope that helps. This is the way I understand it. If you have a different understanding, good on you. Anyway, take care. Sorry for the length again, but I'll see you next time. Bye.